Welcome to the SETI Colloquium series. We are extremely lucky today to have Konstantin Batygin from Caltech give us the colloquium. Konstantin is, so to say, native of the area. He went to undergrad at UC Santa Cruz. Then he was a graduate student in Caltech, advised by Mike Brown and David Stevenson. Then he did his postdoc at Harvard, but then came back to LA, and now he's faculty at Caltech. And today he'll tell us about Jupiter's grand attack.
All right, thanks, Mattia. Yeah, and it's a pleasure to be here at SETI. This is actually a lot like coming home for me. I was actually a high school student in San Jose, so the Bay Area always associates with good times for me. System and sort of start out with a brief fairy tale which will outline all of the important events that occurred in the last 4.5 billion years. So we started out as a giant molecular cloud, and inside of which the sun formed, surrounded by a circumplanetary disk. Within this gaseous disk, some planets formed that were gaseous: Jupiter, Saturn, Uranus, Neptune, which have a somewhat diminished amount of gas. Then the terrestrial planets formed. Then our planets went unstable, we think, for a little while, maybe caused the late heavy bombardment. And then we won the war on dinosaurs with the help of a 10-kilometer planetesimal. So thanks for the planetesimal there. And then the Beatles formed. And then the sort of offspring proved that SoCal punk is sort of the most superior form of punk. So now we still have about an hour to go, and we're almost done with the story of the solar system. So we might as well go into a little bit more detail here. So we, like I said, started out as a giant molecular cloud. This is a real picture. Yeah, like you said, it's giving us the finger. It's like, what? Here you go. Hello. So these molecular clouds, this is a simulation by Matthew Bate of one such molecular cloud, in time cool, develop over densities. Here the yellow, sort of the bright regions are the dense parts of the molecular cloud. And in the densest parts, they begin to collapse, right, and form stars. So these little regions here are like star factories. And as you can see, you can produce quite a large number of stars per such cloud. Numbers on the order of 1,000, 10,000 are not uncommon. So when this process of gravitational collapse happens, it is subject to the same law of physics as a ballerina who jumps with her arms out and then brings her arms in, spins up. So sort of the random rotational motion of a big, collapsing cloud of gas has to conserve its angular momentum. And the way that nature takes care of this process is it puts about 99% of the mass into the central star, in our case, the sun, and puts all of the angular momentum, all of that sense of rotation, into the circumstellar disk, right, which hosts about 1% of the mass. So there's this kind of 1% dichotomy, right? I mean, it's a little bit like wealth distribution, actually. The 1% gets all the mass, and everybody else is stuck taking care of the angular momentum. Now, within the gaseous component of the nebula, within the nebula itself, there's again this 99 to 1% differential. 99% of the mass of the nebula is comprised in hydrogen and helium gas. 1% is comprised in solids. Anything heavier than helium is considered metal. So how do we think planetesimals form? Well, actually, in the last decade or so, there's been tremendous progress with a lot of new ideas put forward on formation of planetesimals. One such idea actually resembles very much the process, or at least qualitatively, resembles the process of formation of stars, in that it involves gravitational collapse. here's a simulation of the solid dust in a sort of local shearing box within a protoplanetary disk, right? Here stuff is shearing by due to Keplerian motion, Keplerian orbit. What's happening is that dust is actually doing the same thing that tumbleweeds do when they cross the road. It's collecting in these aggregates to try to minimize its overall surface, its overall cross section, right? So it's doing the same thing that also say, bikers and Tour de France do, right? They all want to get together in this clump. This is not because they're all great friends. This is because they're trying to, all ride together, minimize the overall, air resistance that the whole group encounters. Now, what happens is this cannot go on forever. Once the clump becomes massive enough, it collapses under its own gravity, forming objects, which are shown here as these little dots. Now, the attractive part of this theory is actually it generates planetesimals whose peak masses are similar to that of the biggest asteroids, and it completely avoids the whole formation process, right? You just go from millimeter, centimeter pebbles to 100-kilometer planetesimals in one go, because it just goes like that and forms stuff. So we at least believe that there's some traction to this idea. Much remains to be worked out, but it's very promising. So this process of accumulation of pebbles actually continues once the big planetesimals form, right? They don't just form and say, you know what, I'm done growing. They continue to kind of feed off of their local neighborhood. And again, it has been shown, this is simulation from Michael Lamberts and Anders Johansson from last year, has been shown that formation of planets is actually a rather rapid process if we believe this story. So once you collapse and form planetesimals, to grow to something like an Earth mass is only 1,000 years, right? So you go from a 100-kilometer object to something like an Earth mass in 1,000, 10,000 years, just because this accumulation of pebbles is very efficient, and it's aided by the fact that they're all submerged in gas. So objects continue to grow. Eventually, they reach a point. Before I get to that, I should continue on with my fairy tale about the solar system, and sort of point out that in the solar system, we believe, or at least we are told, textbooks say, that this process only happened beyond about 3 astronomical units, right? So, and this assertion really comes from taking the masses of each of the planets, grinding them down into neighboring annuli, and trying to reconstruct what was the mass surface density, what was the profile of the disk from which the solar system formed. Now, in the solar system, we have Jupiter, Saturn, Uranus, and Neptune, the big boys, living beyond 3 astronomical units, and 4 relatively low mass terrestrial planets living interior to 3 astronomical units. So it was kind of naturally assumed that there's a clear break in the solid surface density of the nebula, and this break is attributed to the fact that beyond 3 astronomical units, ice can condense, so you can make pebbles out of little ice balls, whereas inside of 3 astronomical units, it is only the silicates, it's only rocks that condense, and there is definitely more water in the universe than there is silicon. So that was kind of that's called the minimum mass solar nebula, the most famous example of which was reconstructed by Hayashi in 1981. There are other variants of it. So what about these guys, the cores of Jupiter, Saturn, Uranus, and Neptune, as they were forming where in this part, this latter, this faraway part of the disk? I'm just sort of told we have to keep all the questions till the end because of the video or something. So hold that thought. All right. So what about these cores that form, right? They grow. Eventually, they reach a critical mass where they begin to actually influence gravitationally the gas around them, right? And the gas around them begins to gravitationally back react on the planets that are forming themselves. This causes their orbits to change in time. So for planets less massive than Saturn, what happens is the planets kind of develop a wake in the gas. This wake is qualitatively not too different from the wake of a boat. If everyone has been on a boat or at least seen a boat, you know that a boat, as it goes through water, makes a wake. This is sort of like the wake, gravitational wake associated with a planet. And it develops these spiral arms, which then back react. They pull on the planet. Except for because of Keplerian shear, here things are going faster. They're orbiting faster than the planet. On an orbit further away from the planet, things are orbiting slower. So this wake gets advected forward on an interior orbit and backwards on an exterior orbit. Now, the reason that this leads to a change in the size of the orbit of the planet is because this forward part of the wake is gravitationally pulling on the planet. It's trying to give up its own energy, right? Trying to pull the planet forward, right? Because gravity is attractive. Gives up its own energy. Planet gains some energy and actually walks out of the solar potential well. So weirdly enough, in a Keplerian disk, even though gravity is an attractive force, it almost acts as a repulsive effect. So this part of the wake ends up pushing the planet away. And the reverse is happening for the outer part of the wake. The outer part is trying to retard the motion of the planet, slow it down. Okay, but by slowing down the motion of the planet kind of falls towards the sun, so its orbit shrinks. So there's this tug of war. And it turns out that the outer wake in the isothermal limit, locally isothermal limit, wins by a few percent. So the overall migration motion is interior. I should mention that this is sort of the simplest version of the picture. The full calculation is much more complicated. The full three-dimensional calculation is much more complicated and depends on things that we don't know very well. So, but overall, this is sort of the qualitative story we have. Once you form a core, that core will tend to migrate inwards. Now, if a planet manages to grow up to a size, or rather mass greater than that of Saturn, say a mass of Jupiter, it can actually dominate its own orbital neighborhood. And what will happen, this is in a frame co-rotating with the planet. So the planet is not really standing still. The camera is moving along with the orbit of the planet. What happens is the planet can clear out a gap, okay, in the disk. And what it does is it positions itself in sort of the center of the gap where the outer and inner torques instantaneously cancel, and then just gets kind of flushed inwards along with the accretionary flow of the gas. So as the gas slowly sinks onto the star due to its viscosity, the planet is sort of along for the ride. The important thing here is this mode of so-called type 2 migration. These are not the most creative names, by the way. Type 1 and type 2 migration. We really could have done better. But anyway, that's the convention now. This mode for more massive planets that open gap is slower than for those that do not. Okay? So those that are completely submerged in the gas run away inwards faster. Now, what do we have in the solar system to leading order? To leading order, we have the Sun, Jupiter, and Saturn. Right? If we kind of make a mass cutoff and say anything less massive than Saturn doesn't count. And in fact, it was the first, it was the very first, I think, simulation, hydrodynamic simulation of just putting the sun, a gaseous disk, Jupiter, and Saturn that discovered the following effect. Right, now, individually, note, all that would happen is you put down Saturn, it will just get flushed towards the sun. You put down Jupiter, it would also get flushed towards the sun. We would have either no planets or a planet very close to, orbiting very close to the sun. Instead, the following picture occurs. So Jupiter slowly moves in, and Saturn eventually catches up to Jupiter's orbit from further out. But it doesn't really catch up to Jupiter's orbit per se. It catches up to an orbital configuration known as a resonance, where Jupiter's orbital period is 3/2 shorter than that of Saturn. So per 3 revolutions around the sun that Jupiter makes, Saturn goes around twice. This sounds a little bit like numerology, but it's not. It actually is sort of the same fundamental physics as why when you're trying to push a little kid on a swing, I have a little kid, so I know this, you want to push only once or twice per oscillation cycle. If you push 50 times in random directions, kid's going to cry. So you have to, in order to transfer energy efficiently to the child, right, the perturbations have to be coherent. And this type of a resonant configuration where the orbital periods can be represented as a ratio of subsequent integers is a configuration where the planets can gravitationally perturb each other coherently. Right? They start sharing their angular momentum and energy budgets. They lock, they get married, you can say, and then they act as a unit. Now, what happens in time is that the two planets clear out a mutual gap. Okay? And now the torque balance that is established is different. Right? Whereas before we just had, for Jupiter, the outer disk pushing on Jupiter, the inner disk pushing on Jupiter, and the outer disk wins. In this case, the outer disk is now trying to push Saturn inwards, and the inner disk is trying to push Jupiter outwards. Jupiter is more massive, so now the inner disk wins. Right? So this locking into resonance, and owing to the particular mass ratio between Jupiter and Saturn, allows our solar system's gas giants to actually reverse their inwards drift. Right? So individually, they'd be flushed towards the sun, but the two of them lock into this configuration, shift into reverse, and slowly plow back out.
Does Saturn open a gap? Before you said no, now you're saying yes?
Saturn opens half a gap. Right? Saturn is on the limit, right? So Saturn, actually, the 3-to-2 resonance is well inside Jupiter's gap anyway.
So it doesn't open a gap?
Not really, a weak gap. So we'll run the simulation forward. The planets grow back out, right? Their orbits increase. And this, again, rather unfortunately, naming-wise, is called the Grand Tack. I should point out that this effect was discovered in 2001, to give credit where it's due, by Frederick Massey and another person by the last name of Snellgrove. So what their initial kind of motivation for this was to explain why Jupiter and Saturn are where they are today. How did they remain at these large orbital radii, in face of inwards migration? In 2011, this was made somewhat more famous by a group out of the Nice Observatory led by Kevin Walsh, who showed that this has an interesting consequence. Namely, it's that this inward then outward migration of Jupiter aids with the formation of the terrestrial planets. So a problem that had plagued the field of terrestrial planet formation for many years is actually that you kind of make a nebula, make a solid, put down some solid material, allow it to grow, you tend to get the same sized planets. But Mars is a factor of 10 too small, right? Mars is a factor of 10 less massive than the Earth or Venus. So that was a problem. Well, it turns out this inward-outward migration of Jupiter is a way to resolve that issue, because we don't know where Jupiter turned around, right? Any number is as good as any other. 2.874 is as good a number as 2.1, is as good a number as 1.5. But if we choose sort of Jupiter's turnaround orbit to be at 1.5 astronomical units, roughly where Mars is today, what happens is Jupiter is able to gravitationally confine the solid component of the inner part of the disk into a narrow annulus. Okay? Now, ignore the fact that this annulus is truncated also from the inside. Okay? This is completely artificial. For a long time, the excuse here was that because orbital periods are fast, codes are not able to resolve orbits very many planetesimals. That's actually not true anymore. It's probably true in 1990 something. So long story short, just ignore the fact that nothing formed here. We've got no planets inside, so nothing formed here. But if you just kind of buy this confinement of the solid component of the inner nebula between 0.7 and 1.25 AU, then you reproduce a relatively nice looking solar system. I think this is a simulation from the original 2011 Walsh paper. What happens is basically this annulus diffusively spreads. It's like putting silly putty in a tower and watching it spread apart. What we obtain is two big planets kind of in the center, and then the edges of this diffusively spreading system are occupied by small planets. Okay? So we can reproduce the small mass of Mars. So that was a pretty big deal. Right? This is kind of an unintended consequence of this model. You might say, at this point, that I have lied to you because you know the orbital periods of Jupiter and Saturn, or you happen to have Wikipedia handy, and you say, I know what they are. Their ratios are not 3:2, right? In fact, they're closer to 5:2. Right? What's going on there? So we, again, think we sort of figured out what happened. We think they started out compact. In fact, we think the whole outer solar system started out compact in this chain of orbital periods that were rational with each other. Furthermore, we believe there was a disk of debris which started beyond Neptune's original orbit, went to about 30 astronomical units, Neptune's current orbit. So watch what happens. If we just let the system go, all that's happening here is that the planetesimals and the planets are pulling on each other gravitationally. There's no additional magic. The system kind of hangs out for a while. The orbits slowly spread apart because Neptune is gravitationally scattering some of the planetesimals inwards, so they're exchanging angular momentum. Eventually, what's going to happen is Jupiter and Saturn will encounter a resonance from the wrong direction, and all hell will break loose, right? So the whole system scatters, right? And the ice giants just jump to their current locations. Now again, remember, there's no kind of prefabricated information about the solar system here. This is just a simulation which starts out with a compact set of planets, a disk of debris, and what we end up with is actually quite reminiscent of our own solar system. Moreover, this process places all of this debris into a region which we now know as the Kuiper belt, and actually does a pretty good job reproducing the dynamical structure of the Kuiper belt. The end, right? We have covered it all, and we have solved, right? We have a completely bulletproof story for how the solar system formed. Right now, let's see how this compares against the Exoplanetary Catalog. Right, so here, in this plot, all of the colored dots are exoplanet candidates detected by the Kepler spacecraft. Okay? Their size is indicative of their physical size. There's a legend here. They're all a little bit, on average, a little bit smaller than Neptune. This is plotted on a log scale, right? And here are the orbits of Mercury, Venus, Earth, and Mars. Okay? So it appears that our solar system kind of missed the mark a little bit, right? We have nothing inside of Mercury's orbit. There have been searches for so-called volcanoid asteroids. They're just not there. Right? There's just nothing there, no rocks, right? But turns out inside of Mercury's orbit is the most populated place around other sun-like stars. Right? This is what we have come up with. Yeah.
Could there be some
Selection bias. Okay, very, very good point. Indeed, Kepler is a transit-based telescope, right? So it needs something like three transits to decide that this is in fact a periodic planet. Even accounting for this, this is much too compact, right? So the fall off in the gradient is faster than what you would expect if it was just a continuous population and accounting for detection bias. So absolutely there's a detection bias, and absolutely we don't know in the Kepler sample what lives beyond 1 AU, okay? In fact, we don't even know very well what lives at 1 AU in the Kepler sample. But still, this tends to be much too compact. This is a real effect. And these guys are found around half of sun-like stars, right? Now, you might say, well, the solar system belongs to the other half, right? Well, okay, it actually, you would be right, it does, in that we don't have any planets inside of Mercury's orbit. In making that statement, however, it's important to kind of discount about 25% of that remaining half due to binary stars. We don't know why very well, but work that, for instance, Adam Krauss at University of Texas in Austin has been doing suggests that planets don't come around as often in long-lived binary systems, so which account for about 25% of that missing hole. So we have the remaining 25% to fill, and in that remaining 25%, I just want you all to keep in mind that giant planets like Jupiter and Saturn are found around approximately 15% of sun-like stars. Now, the argument I'm going to make is that actually that 15% that have Jupiter, Saturn-like planets don't have this inner population of objects. The poster child of this whole population of newly discovered super-Earth, this newly discovered galactic census, is called the Kepler-11 system. It's really pretty awesome, right? It's got 6 planets, 5 of which live well inside of Mercury's orbit, and the 6th kind of just grazes Mercury's orbit. So it's exceptionally compact, and its mass in total is something on the order of 30 or 40 Earth masses. I don't remember exactly, but I think it's on that order of magnitude. So it's exceptional. We have, more than 20 times the amount of mass stuck inside, the inner bound of our solar system. So you can do the same exercise as the Hayashi 1981 reconstruction of the solar nebula. You can just take each one of those planets, break them apart, kind of statistically, try to reconstruct an average extrasolar minimum mass nebula. And this was done by a few authors, most recently by Eugene Chang and Greg Laughlin in 2013. What they obtain are these blue lines. Now, should minimum mass nebulae be taken very seriously? Probably not, right? Because of migration, which we discussed earlier. But one thing that we can immediately learn from sort of this extrasolar exercise is that there isn't this drop-off, right, that was inferred for the solar system. For the solar system, we have this immediate drop-off in mass, interior of 3AU. The extrasolar version of the minimum mass nebula actually matches on pretty well to the outer part of the solar nebula, but is substantially more massive in the inner region. So I would argue that we've learned many, many things in the recent years with the triumphant success of the Kepler mission. But one of the key things that we have learned is that relative to other sun-like stars, right, the solar system's terrestrial region is very poor in mass. Right? We're missing mass. There should be more stuff. So one way to attack this problem is to try and figure out a way by which the solar system did not form these objects. Right? And say the solar system had something special going on, and the inner region just kind of decided that it was either not going to form objects or it was not going to retain them as they migrated in. I think that's a little bit dissatisfactory. Right? Instead, we have to look at the story that I've foretold about this fairy tale about the formation of the solar system, because after all, a lot of effort went into constructing that story. A lot of constraints in the solar system are matched by that story, and see if there's some unintended consequence of one of those processes that are already in place that can explain the lack of close-in planets close to the sun. So our proposition is going to have a total of 4 components. We're going to examine this long-range migration of Jupiter and Saturn that I discussed already in some detail, right? We're going to have gravity in our model, as we should. Gravity is there, right? So what this is going to lead to is orbital excitation of planetesimals that are going to be swept up by Jovian resonances. As I will argue, these planetesimals tend to be excited to the point where they suffer destructive collisions, and these destructive collisions will generate a population of less massive planetesimals, which will push the super-Earths into the sun. That's the story. Okay, so let's examine what I'm talking about. So we've got sort of a schematic here. The orbit of Jupiter is shown in this line. Interior to the orbit of Jupiter, there will always be some orbit where the period is twice as short, right? That's the location of the 2-to-1 resonance, approximately speaking. Imagine that there's a planetesimal, a planetary building block, a small body which lives immediately inside of that orbit. As Jupiter's orbit shrinks, that planetesimal will be swept up by the resonance. It will all of a sudden start to feel coherent perturbations by Jupiter's orbit. Okay? And just like the case of Jupiter and Saturn, which I showed before, this will entrain the planetesimal in resonance, and the planetesimal will start decreasing its orbital size in concert with that of Jupiter. Now, adiabatic invariance tells us that you cannot decrease the size of your orbit for free, right? You have to pay a price. And that price turns out to be enhanced eccentricity. So as the orbit shrinks, it also becomes more elliptical, okay? And that's just, for the 2-to-1 resonance, all it has to do is follow this expression. It has to conserve that expression where semi-major axis is A and eccentricity is E. So we did the following numerical experiment, right? We took a numerical code, we put Jupiter in. Jupiter is going to migrate inwards on a time scale of 100,000 years. That's what we get from that previous picture with the gas. We're going to populate this entire inner region by planetesimals with a surface density profile that goes inversely with radius. That's what the latest observations suggest. And all of these planetesimals will also be subject to feeling aerodynamic drag. Right, so they're going to be, as they orbit in the nebula, they're going to feel a headwind if they orbit faster than the gas around them, right?
Individually or as a group?
Individually. Each object is feeling its own.
But they act like a plate, so this is not right. This has to be as a group.
No. The cumulative mass of the planetesimals is less. But let's keep, we have to keep questions till the end. So we'll talk about that. Let's see what happens. Here's a numerical simulation. Jupiter is the white line. The cyan lines are those objects that live inside the resonance zone. Okay? The gold lines are those that live interior to the 2-to-1 commensurability, so they do not, that are not perturbed by Jupiter substantially. So we let time go forward, okay? And as I sort of said, what happens is these resonant guys get their ellipticity, their eccentricities excited, and in time, they start to overlap the yet unperturbed part of the disk. So this is just a movie which is an outcome of the simulation that we did. We can keep on watching this for a long time. If we watch it long enough, I'm pretty sure I could get you all to give up your credit card numbers to the Nigerian prince or something like that. So let's kind of we can fast forward. It's pretty mesmerizing to watch. I sometimes watch this just for no reason. So here's a picture, same representation of the same process. This is just intended to show you that the capture and resonance is actually a rather efficient process, right? So these guys come in and they get stuck at orbital periods, which are 2, 3 halves, 1, and very rarely do they run through the orbits of Jupiter and get scattered outwards. Right, so it's pretty good. They cannot grow their eccentricities forever, ultimately, okay, because they're being aerodynamically damped, right? So once they reach a critical eccentricity, there's this balance between Jupiter's adiabatic excitation of their eccentricity and the gas drag facilitated damping, right? So this is, and that process, of course, depends on the size that we assume for the planetesimals. So we did this experiment for 3 different planetesimal sizes that are kind of characteristic, or can be taken as characteristic. Our nominal model is that for 100-kilometer bodies. This is kind of what you get from that story of dust collapsing to make planetesimals. They'll get excited about 0.3, 0.25, something like that. You can do this for lower mass objects, 10-kilometer bodies. Now 10-kilometer bodies are smaller. They feel.
Can you review the color scheme again?
Yes, thank you. The color scheme is actually indicative of the original location. So it goes from red to blue in the original semi-major axes. So actually it's better shown on the next slide, which is 1,000-kilometer objects. So it's these red objects which start out here at about 4.5, get carried all the way up here in eccentricity semi-major axis space. And so this whole thing kind of is doing that. So objects that are bigger get excited to higher eccentricities. That's the key of what I'm trying to say here. We can calculate the kind of order of magnitude collision frequency that we would expect in such a collisional front that Jupiter is driving, right? And this is pretty easy to do. What we obtain is actually a highly collisional system, something like 22, something like a collision. So every object suffers a collision once every 20 to 2,000 orbits. So they really bump into each other a lot. This is actually aided, weirdly enough, by the gas drag, because what happens is as the eccentricities get excited, right, the gas tends to confine the objects more to the midplane of the disk, because inclinations do not get the same excitation from Jupiter as eccentricities do. So it's kind of taking this entire population of planetesimals and confining them, thereby also increasing their collisional frequency. So what happens when two things collide in space? Well, they have two choices. Well, three really. They can bounce, they can join and accrete, or they can break each other apart. How do we know which happens? Well, this, as most things, can be gotten from a YouTube video. So there's a hipster with a guitar. He kind of tries to break it. The first time is kind of wimpy, doesn't do anything. But the second time, he's mad. He really goes for it, and his guitar just blows up. And there are pieces of it. They're coming off. I'm not actually sure why it blew up with smoke, but it's cool. Like there are pieces flying off of it. Like the guitar just breaks apart. So it's kind of almost intuitive that the outcome of a collision depends on how hard things collide. In other words, it depends on the specific energy of the collision. And we have a pretty simple to use expression for as a criterion for when things become break apart and when things accrete. So if the specific energy of the impact, where m prime is the mass of the bullet that's coming in, big M is the mass of the target, times their velocity, their encounter velocity squared over 2, exceeds this quantity here, where rho is density and r is the size, then the objects break apart into two pieces or more. Okay? So we can just use the outcome of our calculations, right, to estimate the encounter velocity as the product of Keplerian velocity and eccentricity to an order of magnitude that's okay. And we just plug in for the right-hand size rock density and size of 10, 100,000 kilometer planetesimals. And it turns out, roughly independently of what size planetesimal you pick, the impactor to target mass ratio of about 10% yields fragmentation. Okay? Why is it independent? Well, remember I said that big objects are excited to higher eccentricity. So even though they're big and they have more binding energy, they collide with each other harder, so to speak. Right? So across the board, you only have to encounter something that is 10 times less massive than you are to break apart in two. This means that the collisional front that Jupiter is facilitating is one that is destructive and is grinding down the population of planetesimals from 100 or 1,000 kilometer objects to ones that are much smaller in size. As the size of the object, this rock that's being ground down, decreases, more and more these planetesimals begin to suffer the effects of aerodynamic friction. Right? So we know, again, from intuition that if I took a tank and threw it, it would fly much further than if I took a feather and threw it. Right? This is effectively because a tank has, well, a lot more inertia. Right? Now, the gas is always orbiting at a somewhat sub-Keplerian velocity. This is because the gas is taking advantage of radial pressure support. It doesn't have to orbit as fast to keep up with the sun's gravity, right? And that difference really is quite small. It's about 0.5%. But it turns out to matter quite a bit when the rocks that are produced start flirting with sizes of order a kilometer or smaller than a kilometer. Right, and the well-known formula for the acceleration of a particle felt by gas drag is proportional to its cross-sectional area squared. This makes sense, right? If I'm skydiving, if I go like this compared to if I go like that, I'll be falling slower. But it's also inversely proportional to the mass, which is proportional to the cube of the size. So the whole thing scales as 1 over size. Right, so the smaller that you are, the more acceleration you experience. So, I can't help myself with these things. I love YouTube. So here's an example of that exact process. We had a bunch of ducks. and the wind blew, and see, all the little ducks are being carried away where the big duck gets to stick. Well, not anymore. So the wind gets strong enough, and then it takes a bath. But see, the little guys, they just keep going. And no ducks were harmed during the making of this video. So we're kind of okay on the PETA front. So we think, in particular Greg Laughlin and I think that the same type of process which the ducks just experienced in the video is responsible for flushing the pre-existing super Earths in the solar system into the sun. Let's see what we have, the kind of picture that we have. So I already discussed the Kepler 11 system. It's the poster child. What I'm going to do is, just for fun, I'm going to take the Kepler 11 system and I'm just going to place it in the inner solar system and imagine that at the time when Jupiter and Saturn were migrating in and out, these planets, which we now know are the results of the dominant mode of planet formation, actually existed in the solar system. I mean, why not? Why should the solar system be exempt, right? It doesn't have that tax status. All right. So we have the Kepler 11 analog, not actually suggesting that the super Earths of the solar system were exactly like Kepler 11, had any resemblance to Kepler 11. I'm just using Kepler 11 as a tangible example because everyone has a poster. I hope everyone has a poster with Kepler 11 on it. Right, so Jupiter is done with its migration. It's going to come back out, and it leaves behind this front of particles, which are all smaller in size, so their orbits are going to shrink. All right, let's see what happens to our Kepler 11 system. First thing is I'm going to use advanced technology. I just learned how to do these zoom-ins on Keynote, so I'm really excited about that. We're going to zoom in onto the Kepler 11 system. There's, in gray, for reference, Mercury's current orbit. Okay, and then the color is going to change, and now the simulation is going. So now, from the outside, what's going to come in are some gold lines. Those gold orbits are representing the orbits of the planetesimals that are decaying. And I wish I had some ominous music for this, because it would sort of make the story better, but you're going to just have to play it in your head. Choose your own, death metal. Right. So what's happening here is actually a repetition of the same type of process that we already saw before. These guys are coming in, and they're locking in exterior resonances with the super Earths, and now they're pushing on the super Earth to they're entraining the super Earth, so to speak. Now, the cumulative mass here is approximately 5 Earth masses. So, it has to be flirting with the total mass of the inner system. But as time goes on, and this whole thing is about 50,000 years, right? What's going to happen is all of these planets are just being flushed inwards, right? And they decay onto the surface of the sun. Okay. Great question. So there we used 100 kilometers. I should have mentioned that planetesimals, once they grind down to about a kilometer, they start running away inwards faster than Jupiter is trying to sweep them up. So Jupiter sweeps them up at first when they're big. They break apart, and then they run away inwards. So Jupiter is no longer able to entrain them. That's why it's sort of a continuous process. In this talk, I have imagined it as almost being discrete. First Jupiter grabs them, then they all break apart, then they flush the planetesimals in. In reality, it's all happening at the same time, roughly speaking. Now, here it's the same outcome of the simulation, just plotted in a different way. We have time on the x-axis, orbital radius of the Kepler 11 analog in the solar system. On the y-axis, the thickness of each line is representative of the orbital eccentricity, namely the furthest away point on the orbit and the closest endpoint to the sun. So all in all, the orbits stay pretty circular throughout this whole process, as you already saw. So what is the kind of cool thing about this whole story. And how do we connect it back? I think the way that it connects back to this fairy tale that I started out with. So remember I said nothing formed in this inner region, right, in this 0.7 AU region. Maybe the reason that the solar system's forming material was confined between 0.7 and 1.2 astronomical units was because this area here was actually evacuated by the pre-existing super-Earth. And it matches up beautifully to where the Kepler planets live, right? Maybe the fact that we have nothing inside of Mercury's orbit, and the fact that in order to reproduce the solar system, we have to confine all of the material in a narrow annulus. It's kind of a smoking gun to what was there before. So that is basically the story that I'm trying to advocate for. I'm proud to say that it made the news and already generated some really well thought through discussion on the common boards. So with that in mind, I would like to summarize what I've told you about. So what did we cover? We talked about how Jupiter's current orbit is actually not representative of where it formed. It is rather a consequence of inward and outward migration, which was facilitated by the presence and resonance with Saturn. The inward phase of Jupiter's migration likely entrained a population of planetesimals into resonances that led to some orbital excitation. And this orbital excitation, in turn, resulted in a collisional avalanche that generated a debris of smaller objects that were aerodynamically shepherded close-in super-Earths onto the surface of the sun. Now, of course, the question lingers of how do we know if any of this is legit? Like, how do we know if this is true or not? We, of course, cannot go onto the surface of the sun and dig out the pieces of super-Earth. There's no direct, as is with much of this reconstruction of the solar system's formation. Actually, geologists run into the same problem with plate tectonics. But the point is, we cannot go and exactly reconstruct what happened in the early solar system. But we can look for signs of the same exact process occurring in the extrasolar planetary sample. So what is a direct consequence of the model that we're proposing? Well, what we're essentially proposing is that if you form giant planets around your star, those giant planets, by this inward-outward type migration, will facilitate the decay of super-Earths onto their star. So the two populations should be anti-correlated at some level of statistical significance. In other words, stars which host Jupiter-like planets should, as a rule, there will of course be exceptions to this, but as a rule, not host super-Earths. Systems with super-Earths should, as a rule, not have a multitude of giant planets residing at orbits beyond periods of 100 days. Another thing that we can do, and this is quite exciting with the onset of ALMA's telescope is really flexing its muscles now, is that we can look for signs of this in process, right? So as this whole thing is happening, right, you're generating a ton of debris, a ton of dust, which is collisionally heated. So disks, protoplanetary disks with substantial gaps in them, should also exhibit signs in their spectral energy distribution of hot dust, right? And that is something that I think has already been kind of hinted at, and I'm excited for this to maybe connect as a link to observation with the story we're providing for the solar system. So all in all, that is basically the end. I hope that this picture can eventually bring us one step closer to kind of viewing our own solar system's architecture in a more galactic light, in a more extrasolar light. All right, I'll stop here. Thank you.
So, okay, I'm gonna abuse the privilege and ask the first question.
Abuse away.
Where you have lots of gas that's affecting planetesimals, which are interacting with the super Earths, do you have type 1 migration?
Excellent question. The answer is no. We did two separate runs. The run that I showed you, the planets themselves are effectively unaware of the gas. Okay, this is because I wanted to kind of highlight the pure, this pure coupling effect between the planetesimals and the planets. We also did a run where the planets' eccentricities are damped by type 1 migration. The results look nearly identical. The reason type 1 semi-major axis damping is not present in any of the simulations with the super Earths is because there's growing evidence, right, that this inner region of the disk is actually, that's where the type 1 torques do not operate because of entropy gradients and all of this nastiness. But I actually don't want to get into that because that's well outside my level of comfort. So of course, if you just put type 1 torques everywhere, you can flush the planets in, but the planets are there. So something is preventing type 1 migration from operating in the inner regions of the disk.
Okay, Matya asked part of my question already, but how are you going to clear out things as efficiently out to the point where you want to clear them out? Is there enough gas that just everything is going to come in at in that part of the disk? Why won't it start accreting? Why won't material remain?
Yeah, so that's an excellent question. Actually, the accretion onto planets was in the model. We didn't see a substantial gain in the masses of the planets as a result of their interactions with the planetesimals. This ultimately what you're asking though is a quantitative question. It depends on what is the exact size distribution of the debris that's generated, and I think that the outcomes here are actually, they can be quite rich. I'm not opposed to thinking about a system where all of this stuff comes in and actually does, while decaying, also generate smaller objects. The whole thing is much more dynamic than we can capture in simulations. But I think overall, you can kind of compute the collisional. You can do the whole formation calculation, and I think that the time scale on which the super Earths get pushed in, on average, is faster than the time scale on which things will reaccrete and grow. Okay?
When Jupiter is migrating in towards the sun, would the moons of Jupiter be warm enough to have liquid water on their surface? And how long would they spend in that situation, roughly speaking?
It's a good question. The moons of Jupiter at that point are actually submerged in their own circumplanetary disk, right? So they're undergoing their own story. Would they be hot enough to have liquid water? Well, they would be presumably undergoing the same tidal heating, the same type of tidal heating they're undergoing now, although I'm really not sure about the tidal quality fact, the efficiency of that tidal heating early on. So I will sort of claim the Fifth Amendment on this one. I'll just say that I'm more or less oblivious as to what's happening to Jupiter's moons. It's not even clear that they had formed yet at the time.
Right, so your entire story here is happening very fast compared to the time at which you remove gas and you need the gas. So you're talking about migration times for Jupiter that are like 100,000 years, you said.
Yep.
So that means there's a lot of gas. So that means that Saturn would not have opened the gap and it would still grow. So you're not matching that constraint, the Saturn constraint. You're sort of staying with the masses of the planets as they are. Now, on top of that, you have this very massive planetesimal disk, which would grow and leave something behind. You can't throw, at some point it starts to, you're pushing things with planetesimals, but pushing that last little bit out is difficult. So the alternative would be simply to say what Mattia was talking about. You have type 1 migration, the super Earths got lost, and then Jupiter became big enough that Jupiter was able to open a gap, and so it survived for that reason. So that would bypass the planetesimals in this story altogether.
So that's actually, the number of very, very good points. This issue of growth of Saturn, I'll start with the first thing you said, is actually that bothers me as well. Ultimately, we know that Saturn is now not as big as Jupiter. So something limited its growth. One of the proposals for limiting its growth is actually the fact that the disk material itself is becoming more opaque as the gas is diminishing, right? I don't want to get too into what I actually don't have a particular stake in it. I will merely say that that's a good question. Now, with respect to the type 1 point that Mattia made, here, I would say that I'm a little bit uncomfortable with the conventional story of the type 1 migration, where planets start out, they just migrate to the magnetospheric cavity of the disk, and then they park themselves inside of that magnetospheric cavity. The planets that we observe around other stars have orbital periods that are somewhat bigger than what we usually consider as the edge of the disk, right? So I think something more is happening. Ultimately, when you get close in, type 1 migration becomes really complicated. There are entropy gradients in the disk, there's turbulence, there's all of this stuff. So I kind of in spirit of Occam's razor and trying to keep the model as simple as possible, I would want to stick to a story where I don't rely on type 1 migration in the inner part of the disk, which is poorly understood.
Okay, just a quick question and then hopefully a little more substantive one. The quick one is, does the time frame in which you're proposing this happen coincide with the late heavy bombardment where the avalanche, or is it a different time period?
It's a different time period.
Okay.
So all of this is happening well within the first few millions of years of the solar system's lifetime. Late heavy bombardment happened hundreds of millions of years afterwards.
Okay.
So actually late heavy bombardment may have been correlated with that phase of instability that I showed towards the end of my fairy tale. There are, however, other explanations for it as well.
Okay, so the more substantive question is, so you're proposing super Earths get sucked into the sun, but the Nice model proposed like Neptune's getting shot into outer space. Is there a way to reconcile these models into a super model?
Yes, yes. So it's the super duper model. So the answer is yes, and actually it all, like I said, it's happening on vastly different timescales. This is all happening in the inner solar system during the first few millions of years of the solar system's lifetime. The Nice model and this scattering of Neptune and Uranus to larger orbits is happening almost 1 billion years after the gas is gone, okay? And the fact that Uranus and Neptune actually retain, right, they don't become hot super Earth, is also because Jupiter and Saturn pose a dynamic barrier, right? They, right, as Uranus and Neptune come in, they can lock into resonances with Saturn and just form this chain. So Jupiter and Saturn really provide, they kind of sculpt the solar system in the sense that they begin to regulate who goes in, who goes out, right? But the whole story is consistent because it's all happening at different times, right? It's a movie where, it's basically, this is Act 1. Nice model is Act 128 or something like that.
Yeah, regarding this anti-correlation, is the Kepler data on Kepler 11 precise enough to determine whether there are or are not giant planets out there?
So Kepler is not, the Kepler data set is not ideal for thinking about this. Why? Because the Kepler data set is biased towards closer periods, right? And Kepler stars are hard to follow up with radial velocity methods, which are sensitive to giant planets. So really, right now, I mean, what I did is I just combed through the existing giant planet catalog, and well, it holds up pretty well. But by pretty well, I mean out of something like 300 giant planets that are in the exoplanets.org catalog. 9 or 8 of them have close-in companions. But I don't want to, claim victory on this yet, because the way that giant planets are detected is you kind of go to the telescope every half a year or so to get a point, right? Because giant planet orbits are so long, right? So you don't have to get, it might be that we're missing these super Earths in the radial velocity sample. What will really answer this question is actually the TESS satellite, which will launch 2017 or 2018. I don't remember exactly. But that guy will get all of these close-in meaning local solar neighborhood systems, which will be easy to follow up with radial velocity. So I think this prediction will have to wait a year or two before it really gets tested.
Okay. So if you have any further questions, you can come up to the speaker after the talk. And I have the honor to present our speaker with a SETI mug where the two alien robots are discussing how weird their solar system is or not. So I thank the speaker again.
All right, thank you all.